Hi everyone, today we are going to solve or drive one-dimensional wave equation. So in wave equation, here you have a diagram. What this diagram says, I will tell you about it later. So first, let's concentrate on okay, first of all, let me tell you what is the wave equation in one dimension. So, okay, not this one. If I tell you about the equation, uh, which we are going to drive, then it is the second derivative equation, like 1 by c square, and second derivative of u with respect to t, and second derivative of u with respect to x. So this is the equation, and here your constant c is t by rho. So this is your equation. Now if we start derivation, then it starts with the assumptions or considerations, suppositions, whatever you say. So consider a small segment of a string between x and del x, of a string between x, okay, between x and del x. And here you can see in this diagram, this purple one, I hope you will be able to see, this purple line indicates your wave, the segment of the string. And we are taking, okay, segment starts from this point and until this point. See, this point is x and this point is uh, okay, let me mention, this is x and this is x plus delta x. These are your points. So for more clarification, I must have to use red color, but it's okay. Now we have assumed a segment of the string. Now, okay, this is your small segment of the string here, small segment of string is here, and on this side we are moving with our assumptions. So another thing in assumption is that the string is not moving horizontal, all of its movement is vertical. So you will say segment, okay, segment is not moving horizontal, and its mass is oh, I'm sorry for that, and its mass is rho and delta x. um, and why it is? Because the deflection is so small that it's make your u, what is u is actually your vibration. So you can say deflection. So deflection is represented by u. So here is another thing which we are going to add in our assumption. Because deflection deflection is so small, uh, how much small? It's small to such extent that your del S becomes equal to del X. Now what is del S? When you look at the picture, um, then this line indicates the change in X from here to here, which is del X, and okay, del S is not mentioned in your photo in this diagram, but that is the distance. S is actually the distance which the string has traveled, and del X is horizontal distance, and this is the other term for the distance. And he says that since there is no horizontal movement, that is why whatever distance the string has covered, that is vertical distance. That is why del S is equal to del X. Now we are going to write mass. So you know mass of the string. Okay, this is your mass. In this we have replaced del X with del S, which we just have proved that our del S equals to del X. So in the previous mass we have made an amendment, and now we have del S here. Now if we talk about the acceleration of the string, since it's moving, there's a motion, so certainly there will be some acceleration. And acceleration, wait for a minute, there must be a displacement here. So displacement is equal to d, and d is equal to u. So here we have defined our variable, our main variable in all of this modeling is u, and he says that u is dependent on x and t, and he defines u as displacement. And now we talk about acceleration. So acceleration here in this string, in this segment, acceleration of the segment, that is, certainly you know acceleration is always represented by a formula, term and symbol a, but the differential form of acceleration is this. Here we have used our mentioned variable u, and all of these things equals to a. And here we are trying to see the total force, so we will say sum of the vertical forces, since there is no horizontal force, so sum of the vertical forces along the segment, along the segment is represented by f, and f is equal to t sine of beta minus t sine of alpha, and you can take t as a common, sine beta minus sine alpha. Okay, and here you need the diagram again. If you see in the diagram, this is your t sine alpha, okay, sine beta and sine alpha. So see, this is your sine alpha in the green, and okay, let me just mention it. So here is your sine alpha, and here is your sine beta. See, there is no force along the horizontally. There is no force acting horizontally. So this thing is 0. The magnitude of this is 0, and the magnitude of this is 0. So the only forces which we are going to consider are the sine acting, which are the sine component of the angle. So here you can see t sine beta and t sine alpha are the components that we are going to consider in our model. So after considering uh, the horizontal components in our model and writing the first equation, we are going to consider Newton's second law. I hope you might know then that in this sort of modeling in the applied mathematics, how we derive an equation, we usually consider all of the given data and then we consider all of the relevant laws which we have, and then we try to formulate an equation. So same is the process here. Until now we were seeing what data we have, and now we are trying to see what laws we have to follow here. So since it's motion, we have Newton's second law of motion here. It's very famous. F is equal to ma, and here our a is redefined in terms of u, okay, and here we have t. So from here you can replace the value of mass. What was our value of mass? We had this one, okay. So you got a new equation here, and other thing that you know is recently you defined force in terms of the components, sign components. So if I rewrite that thing here, I know that here my force was like sine in the sum of horizontal components. So now I got a new equation here. So another thing that we know is that deflection of the string and the slope of the string are small, which means alpha and beta are so small that you will have here you have a new concept. We are going to substitute the values of sine alpha and beta. What are sine alpha and beta? We don't know yet. From within this equation, it's there is an ambiguity. You are not you can you're not sure about the sine beta and sine alpha. So for that, we see that since the deflection of the string and the slope of the string are small, of the I think he must use segment, but okay, of the string and slope of string is small, and hence alpha and beta are also small, which means okay is small, you can say, which means alpha and beta, which are the angles, are also small. So mathematically you can write sine alpha is approximately equals to tan alpha, and your sine beta is approximately equals to tan beta. How this happens, let me help you visualize. You know, in the triangle, say this is your Okay, suppose this is a triangle, and within this triangle you have sine alpha, sine beta. So this is your sine alpha. Okay, let me make it. Okay, alpha. So from this diagram you can get the idea of what's happening here. When your horizontal, you can say this side, the perpendicular side of your triangle gets smaller, your hypotenuse also starting to get smaller, and eventually when this sine alpha is equal to 0, your tan alpha becomes equal to cos alpha. So when the cos alpha becomes equal to 0 and becomes very small, uh, your tan alpha becomes equal to sine alpha. So here is the case in which your cos alpha, your horizontal deflection, is 0. That is why these two sides, this perpendicular and hypotenuse, becomes equal to each other. That is why you can see here your sine alpha and sine beta became equal to the tan alpha and tan beta, which means your perpendiculars been have been become equal to your what is your hypotenuse. So from these you can write this thing equals to the first derivative of u with respect to x, where u is dependent on x and t, and this is again the first derivative of u, and u is dependent on x plus delta x and t. Why is it? You know, your the location of sine beta and location of sine alpha. This is based on the location of sine alpha. In at the location of sine alpha, what is your deflection? The rate of deflection is this one, and at the point of sine beta, the rate of deflection is this one. So now I'm going to. Okay, this is not the rate of reflection, it's actually the proportional change, the proportional deflection with respect to your distance. So now it implies that your acceleration, this was your acceleration, is equal to, I am replacing the sine alpha and sine beta in the above equation. So you will have delta u by delta x, and x plus delta x t subtracted by delta u by delta x, and here you will have x and t, and this is nothing. Okay, so here if you divide both sides by delta x, you are going to have the definition of derivative on your right side. So dividing the equation by delta x, we obtain what we obtain. Uh, First of all, you will get rid of this delta x. On this side you will have rho and the second derivative of u with respect to t, and this thing will become equal to t divided by delta x, and other thing will as it as. Is subtracted by this with respect to x and t. Okay, now you can apply the limits on both sides to complete the definition. So here you do not have x, so that is why limit is not going to be applied on this side, delta t square. You must try taking the limit on taking limit delta x approaches to 0, we obtain, okay, what we obtain, this side becomes equal to limit del x approaches to 0 and then 1 by delta x. Okay, I am taking t out of it, so t is here, and other thing is you have delta u by delta x, then you have x plus delta x t, and then you have delta u by delta x, and here you have x and t. So you got the definition of the derivative, so the right side becomes t delta u delta x square. So if you see it again, then you have almost derived the equation of wave. I am rearranging the equation. You can say by rearranging delta u by delta. Okay, that was actually x here. So you must write rearranging. Okay. So now in the last step, you can write thus the equation, the wave equation in one dimension is 1 by c square, second derivative of u with respect to t equals to second derivative of u with respect to x, where your c square is rho by t. So this was it. This was your this was the derivation of wave equation. Now you can see it here.